So let us discuss question number 1. Okay. So what is given in the question is that if the angular velocity, so the angular velocity omega is given by d theta upon dt of a point moving in a plane curve be constant about a fixed origin. Okay. So let us take this as a curve. Okay. This is our fixed origin. So there is a point, the polar coordinate of which is r theta. Okay. So this is our radial direction because it is along the position vector. Okay. So this is our position vector, and the direction perpendicular to the radial direction is transverse direction. This is transverse direction. Okay, and this is radial direction. Radial direction. Okay, and this is our initial line, and the angle of inclination with respect to the initial line is theta. So this is our point P. Okay, so what is given in the question is that angular velocity of a point moving in a plane curve be constant. This is given as constant about the fixed origin. This is fixed origin. Okay, show that its transverse acceleration varies as its radial velocity. So what we have to show? To show transverse acceleration is proportional to radial velocity. Radial velocity. So what we have studied few minutes ago is that we have expressed radial velocity as we have expressed the velocity component at point B as linear combination of the radial velocity as well as the transverse velocity. Okay, so this is given as dr upon dt into er plus r d theta upon dt into e theta. Okay, so this is the radial component and this is the transverse component. This is radial velocity and this is transverse velocity. Transverse velocity, and this is unit vector along transverse direction, and this is unit vector along radial direction. This we have already studied. Also we have expressed acceleration as d2r upon dt square minus r d theta upon dt whole square into unit vector along the radial direction plus half of plus 1 upon r d upon dt r square d theta upon dt. Okay, this is into e theta. So this is our radial acceleration. Radial acceleration, and this is our transverse acceleration. So what we have to show is that this transverse acceleration is 1 upon r d upon dt r square d theta upon dt, okay, is proportional to dr upon dt. Dr upon dt is radial velocity. Okay, so this we have to show. So let us show this. Okay, so let us show this. So we have transverse acceleration as 1 by r d upon dt r square d theta upon dt is equal to, अब d theta upon dt is constant, so let us place this 1 upon r into d upon dt r square into w. This is omega, angular velocity. Omega is constant. Okay, so omega we can take out. This is omega upon r into d upon dt of r square. This is equal to omega upon r into 2r into dr upon dt. This gets cancelled. So we have 2 omega into, and dr upon dt is radial velocity. And this is transverse acceleration. Okay, so this is our expression. So transverse acceleration is proportional to radial velocity. Okay, so let us discuss question number 2. What is given in the question is that a point P describes with an angular velocity about O, the angular spiral r is equal to a e to the power theta, O being the pole of the spiral. Okay, so this is our O. This is origin. Okay. Opening the pole of the spiral, and this is our distance of this point P from the origin. Okay, and this is our initial length. So let us consider this point P as r theta. Okay, obtain the radial and transverse acceleration. Okay, so what we are having is that there is a point P on this curve, and the angular velocity is constant. Matlab omega is equal to d theta upon dt is equal to constant. Okay, and we have r is equal to a e to the power theta. So what we have, how we have expressed the acceleration? Acceleration is equal to d2r upon dt square minus r d theta upon dt the whole square into unit vector along the radial direction plus of 1 upon r d upon dt r square d theta upon dt into unit vector along the transverse direction. Okay, so this is our radial acceleration, and this is transverse acceleration. Transverse acceleration. Okay, so we have r is equal to a e to the power theta. So dr upon dt is equal to a into e to the power theta into d theta upon dt. Okay, so d theta upon dt is constant. So this is equal to, and a e to the power theta is, this is r. This is equal to r into d theta upon dt is omega. R omega is dr upon dt. This we can write as radial acceleration. Radial acceleration is equal to d2r upon dt square minus r d theta upon dt का whole square. This we can write as d upon dt into dr upon dt minus r d theta upon dt. D theta upon dt is omega. This is omega square. This we can write as d upon dt into dr upon dt is r omega. Okay, minus r omega square. This is equal to omega is constant, so omega into dr upon dt minus r omega square, and dr upon dt is dr upon dt is r omega. So this is equal to radial acceleration is equal to omega into dr upon omega into r omega minus r omega square. This is equal to r omega square minus r omega. This is equal to 0. Hence radial acceleration is 0. Okay, so obtain the radial and transverse acceleration. So now let us find transverse acceleration. Okay, so the transverse acceleration is given as 1 upon r d upon dt r square d theta upon dt. Okay, so d theta upon dt is constant, that is omega. So this we can take out. So this is omega. This we can take out. So omega upon r into d upon dt into r square. This is equal to omega upon r into 2r into dr upon dt. So this gets cancelled. So this is equal to 2 omega into dr upon dt. And dr upon dt is r omega. So this is 2 omega into r omega. This is 2 omega square r. So we have the radial acceleration as 0 and transverse acceleration as 2 omega square r. Okay, so let us discuss question number 3. Solution. What is given in the question is that a particle P describes a curved path with a constant velocity, and its angular velocity about the given fixed point varies inversely with the distance from O. Okay, so let us consider a curve like this, and we have a point P, the coordinate of which is r theta. Okay, and let us take this as a fixed point. Okay, and this is the angle of inclination. Okay, so we have this as constant velocity. So v is equal to constant, and angular velocity angular velocity is omega. So we have omega is equal to d theta upon dt. So omega is equal to d theta upon dt. Varies inversely as the distance from O. So distance from O is r. So this is equal to OP. Varies inversely as OP. So we have this as angular velocity. So d theta upon dt varies as 1 upon r. So this gives d theta upon dt is equal to lambda upon r. Okay. So from here we have r d theta upon dt is equal to lambda. Okay, so we have the velocity is given by has the linear combination of radial dr upon dt into er plus r d theta upon dt into d theta. Okay, so this is radial component and this is transverse component. So the velocity is given by dr upon dt into whole square plus r d theta upon dt ka whole square under root. Okay, this is our velocity and velocity is given as constant. This is constant. So v is equal to under root of dr upon dt whole square plus r d theta upon dt is lambda. This is also constant. So we have this as v square is equal to dr upon dt whole square plus this is lambda square. Lambda square. So dr upon dt whole square is equal to v square minus lambda square. So dr upon dt is equal to v square minus lambda square ka under root. Okay, so this is again constant because v is constant as per question. Describes p describes a curve with constant velocity. So the velocity is constant and lambda is also constant. So this is constant. Let us take this as mu. And dr upon dt we can write as dr upon d theta into d theta upon dt is equal to mu. Okay, let us further simplify this. So we are having is that dr upon d theta into d theta upon dt is lambda upon r. So lambda upon r is equal to mu. So this we can write as dr upon r is equal to mu upon lambda into d theta. This we can write this as like this mu upon lambda into d theta. Let us integrate this. So we have log of r is equal to mu upon lambda into theta plus log of c. So this we can write that log of r upon c is equal to mu upon lambda into theta. So r upon c is equal to e to the power of mu upon lambda into theta. Okay, so r is equal to c into e to the power mu upon lambda into theta. So let us put some assumptions. Okay, so let us put this. Okay, so we have r is equal to c into e to the power mu upon lambda into theta. This is equal to r is equal to c into e to the power k theta. Okay, where k is equal to mu upon lambda. Okay, so this is the equation of equiangular spiral. Okay, so hence the curve is equiangular spiral. Okay, let us discuss question number 4. So what is given in the question? Velocities of the particle along and perpendicular to the radial velocity from the fixed origin. Okay, so we have this as, let us consider a point P here. Okay, and this is our origin. Okay, this is our radial direction. Radial direction. And the direction perpendicular to the radial direction is transverse direction. This is perpendicular direction. So we have radial direction, and the velocity along the radial direction is radial velocity. This is dr upon dt. And velocity along the transverse direction is transverse velocity. That is r d theta upon dt. This is transverse velocity. And the unit vector along radial direction is er, and the unit vector along transverse direction is e theta. So how we can represent the velocity at point P? So velocity at P is equal to dr upon dt. This is radial component into er plus transverse component is r d theta upon dt into e theta. So what is given in the question is that the velocity of particle along. So this is the velocity of particle is along the radius vector. The velocity along radius vector. And this is velocity perpendicular to radius vector. Okay, so what we are given is that the velocity along the radius vector. So dr upon dt is given as lambda r square, and velocity along the velocity perpendicular to radius vector. So r d theta upon dt is given as mu theta square. Okay, this is equation 1, this is equation 2. Let us divide equation 1 and 2. So we have dr upon d theta 1 upon r is equal to lambda r square upon mu theta square. So we have dr upon r cube into 1 upon, this is mu. Let us take mu here, and this is equal to lambda into d theta upon theta square. Okay, so let us integrate this. So we have mu into minus 1 upon 2r square. Okay, so dr upon r cube. This is r minus 3 plus 1 upon minus 3 plus. This is equal to r minus 2 upon minus 2. This is 1 upon 2r square minus. Okay, this is equal to lambda into minus 1 by 2 plus c. This is equal to minus mu upon 2r square equal to minus lambda upon theta plus c. This can be further simplified as um, lambda upon theta is equal to mu upon 2r square plus c. Okay, this is the polar equation of path of particle. Okay, now let us find the radial and transverse acceleration in terms of r and theta. How we can find this? So we have dr upon dt is equal to lambda r square and r d theta upon dt is equal to mu theta square. Okay. So now we are having, what we have to find is that radial and transverse acceleration. The acceleration is given as acceleration is equal to d2r upon dt square minus r d theta upon dt ka whole square. This is acceleration along the radial direction plus 1 upon r d upon dt r square d theta upon dt. This is acceleration along transverse direction. Okay. So what we have to find, radial and the transverse acceleration. So this is radial acceleration, and this is transverse acceleration. Okay. So we have this as radial acceleration equal to d2r upon dt square minus r d theta upon dt ka whole square. This is equal to d upon dt of dr upon dt minus r d theta upon dt ka whole square. This is equal to d upon dt into dr upon dt. Dr upon dt is lambda r square minus r into d theta upon dt is mu theta square upon r. From here we have d theta upon dt is equal to mu theta square upon r the whole square. This is equal to lambda into 2r into dr upon dt minus r into mu square theta 4 upon r square. So this is equal to radial acceleration is equal to 2 lambda r into dr upon dt is lambda r square minus this gets cancelled. This is equal to mu square theta 4 upon r. This is equal to 2 lambda square r cube minus mu square theta 4 upon r. This is the radial acceleration. So we have the radial acceleration as 2 lambda square r cube minus mu square theta 4 upon. Okay, this is our radial acceleration. 2 lambda square r cube minus mu square theta 4 upon r. Okay. So now let us find transverse acceleration. Okay, so let us find transverse acceleration. So transverse acceleration is equal to 1 upon r d upon dt r square d theta upon dt. Okay, so d theta upon dt is given as mu theta square upon r. So this is equal to 1 upon r into d upon dt r square into d theta upon dt is mu theta square upon r. Okay, so this is further simplified as 1 upon r d upon dt r into mu theta square. Okay, so this is equal to mu, we can take out, so mu upon r d upon dt r into theta square. Transverse acceleration. Okay, this is equal to mu upon r into 2 theta into d theta upon dt plus theta square into dr upon dt. Okay, so this we can further simplify as transverse acceleration. Okay, so d theta upon dt. So this is equal to mu upon r into 2r into theta. 2r theta into d theta upon dt is mu theta square upon r plus theta square into dr upon dt. dr upon dt is lambda r square. This is equal to mu into 2 r gets cancelled, 2 theta into mu theta square upon r plus theta square lambda r. We have this as 2 mu 2 mu square theta cube upon r plus theta square lambda mu into r. This is transverse acceleration. Transverse acceleration. Okay, so this we can find radial and transverse acceleration. The radial acceleration is given by radial is 2 lambda square r cube minus mu square theta 4 upon r, and transverse acceleration is theta square lambda mu r plus 2 mu square theta cube upon r. This is radial and transverse acceleration. Let us discuss question number 5. How we can solve this? The velocities of the particle along and perpendicular to the radius vector. Okay, so what we are having is that the velocity is given by dr upon dt into er plus r d theta upon dt to e theta. So this is velocity along the, this is radial velocity, and radial velocity is along the radius vector, and this is transverse velocity, and this is perpendicular to the radius vector. So we are having dr upon dt is equal to lambda r, and r d theta upon dt is equal to mu theta. So we have, let us divide question 1 and 2. So we have 1 upon r dr upon d theta is equal to lambda r upon mu theta. So we are having dr upon r square is equal to lambda upon mu d theta upon theta. So we have mu upon lambda dr upon r square is equal to d theta upon theta. So what we are having is that mu upon lambda into minus 1 by r. This is equal to log theta plus log c. The log of c theta is equal to minus mu upon lambda r. Okay, so we have c theta is equal to e to the power minus mu upon lambda into 1 upon r. So theta is equal to 1 upon c e to the power minus mu upon lambda into 1 upon r. So let us take this as 1 upon c as a into e to the power b upon r, where a is equal to 1 upon c and b is equal to minus mu upon lambda. Okay, so this is the path of the particle. Okay, so let us find the radial and transverse acceleration. So let us write down the expression for the acceleration in terms of radial and transverse accelerations. Okay, so let us find this. So we have acceleration as d2r upon dt square minus r d theta upon d2 whole dr plus half, sorry, 1 upon r d, sorry, 1 upon r 1 upon r d upon dt of r square d theta upon dt into d theta. Okay, so this is radial component and this is transverse acceleration. This is radial acceleration. So what we have to show in the question, show that the acceleration along and perpendicular to the radial vector. So acceleration along is acceleration along, matlab radial acceleration. What we are having is that there is a curve, there is a point P here, P R theta. Okay, and there is a point origin O here, is origin O, and we have the distance. Distance of this point from origin is r. So this is our position vector, r vector. So the direction along the radial is radial direction. Direction along the position vector is radial direction, and direction perpendicular to the radial direction is transverse direction. So the acceleration along, this is the acceleration along, the acceleration along the radial, acceleration along the radius vector is radial acceleration, and acceleration perpendicular to the radius vector is transverse acceleration. So we have this as radial acceleration that is along the radius vector. This is transverse acceleration that is perpendicular to the radius vector. So what we are having is that, sorry, so we have dr upon dt is lambda r. So the acceleration along radius vector is d2r upon dt square minus r d theta upon dt का whole square. This is equal to d upon dt of dr upon dt minus r into d theta upon dt का whole square. This is equal to d upon dt of dr upon dt is lambda r minus r into d theta upon dt is mu theta upon r. From here we have d theta upon dt is equal to mu theta upon r. Okay, so this is whole square. This is equal to lambda into dr upon dt minus r into mu square theta square upon r square. This is acceleration along radius vector. Okay, so dr upon dt is lambda r. Okay, so we have this as lambda into dr upon dt is lambda r minus r into mu square theta square. This gets cancelled. So we have mu square theta square upon r. This is equal to lambda square r minus mu square theta square upon r. This is acceleration along radius vector. Okay, this is being asked in the question like this. Now we have to show the transverse acceleration. So let us find transverse acceleration. So we have this as transverse acceleration is equal to 1 upon r d upon dt r square d theta upon dt, and we have dr upon dt is given as lambda r. Okay, so we can find this as 1 upon r d upon dt r square into d theta upon dt is mu theta upon r. This gets cancelled. So we have mu upon r d upon dt r into theta. So this is equal to mu upon r into d theta upon dt plus theta into dr upon dt. This is equal to mu upon r into d theta upon dt is mu theta upon r plus theta into dr upon dt. Dr upon dt is lambda r. So let us take theta outside. So we have this as transverse acceleration is equal to, let us take theta outside. So mu theta, this gets cancelled. So mu theta into mu upon r plus theta outside we are taking na, theta outside we are taking, and we have r in the denominator. So this gets cancelled. So this is plus lambda. Okay. So mu upon r plus lambda. So we have transverse acceleration. Transverse acceleration is equal to mu theta lambda plus mu upon r. This is transverse acceleration. Okay. So let us discuss question number 6. So the acceleration of a point moving in a plane curve. So let us take a point P. So this is our point P. Let us take this as origin. This is our point P. This is our initial line. Okay. So this is, let us consider the coordinate of point as P r theta. Okay. So it is at a distance of r from the origin, and this is our initial line. Initial line. This is angle is theta. This is our radius vector. Radius vector. So the direction along the radius vector is radial direction. This is radial direction. And the direction perpendicular to the radial direction is transverse direction. Transverse direction. Direction. This is transverse direction. This is radial direction. Radial direction. This is radial direction. So what we are having is that the acceleration of a point moving in a plane curve is resolved into two components. Okay, one parallel to the initial line. So parallel to the initial line, and other along the radius vector. Okay, so let us consider the acceleration along the radius vector as r, and the acceleration that is parallel to the initial line. So this is acceleration that is parallel to the initial line is s. So this angle is theta. So this angle is also theta. So the component of s along r will be, this will be s cos theta. Okay, so the net acceleration along the radial direction is r plus s cos theta. So this means radial acceleration, that is the acceleration along the radius vector, along the direction of radius vector, is radial acceleration, is given as r plus s cos theta, and the component of s along this direction, that is transverse direction, is, this is theta, this is 90 minus theta, that is s sin theta. S sin theta. This is s sin theta. So this is in the negative direction. So in the positive direction, this will be minus s sin theta. Okay, so transverse acceleration will be minus s sin theta. And we know that acceleration can be written as d2r upon dt square minus r d theta upon dt, the whole square. This is the radial acceleration. And we have the unit vector along the radial direction, er, plus 1 upon r d upon dt of r square d theta upon d. This is the acceleration along the transverse direction. Okay. So this is our radial acceleration, and this is transverse acceleration. So we have radial acceleration is given as d2r upon dt square minus r d theta upon dt ka whole square. And this is equal to 1 upon r d upon dt r square d theta upon dt. Okay, so let us further simplify both the equations, and we will get the result. So what we are having from here is that, so we have s is equal to minus 1 upon r sin theta d upon dt r square d theta upon dt. Okay, so this is our transverse. This is the acceleration along the initial direction, that is s. Okay, so what we are having, proved up these components. Matlab ki one parallel to the initial line, that is s. This is s. Sorry. And this component is minus 1 upon r sin theta d upon dt r square into theta dot is d theta upon dt. So this is same as this one. This we can write as minus 1 upon r sin theta d upon dt into r square into theta dot, and the theta dot is d theta upon dt. Now let us put s in this particular expression. Okay, let us put s here. So we have this as so we have from here, from this expression we have r is equal to minus s cos theta plus d2r upon dt square minus r d theta upon dt whole square. This is equal to minus cos theta into s. S की वैल्यू क्या है? minus 1 upon r sin theta into d upon dt r square d theta upon dt plus d2r upon dt square minus r d theta upon dt का whole square. So this is equal to cot theta upon r d upon dt of r square into theta dot d theta upon dt theta dot plus r d2r upon dt square, it is r double dot minus r into theta dot square. This is r. Okay, so this is our acceleration along radius vector. So this is r. Acceleration along radius vector is this expression, and acceleration that is parallel to the initial line is this expression. Okay, so the acceleration parallel to the initial line is s, and the acceleration that is along the radius vector is r. Okay, we will discuss further questions in next particular lecture. Okay, thank you.